This lesson deals with a voltage-controlled oscillator. You can find these notes in the ECE402 ebook in Chapter 6, starting on page 28. Here I have a circuit with three LM339s in obviously three different configurations. Now the LM339 is exactly the same as the LM139, it's just in a limited temperature range. If it begins with the number 3, it indicates the temperature range is from 0 to 70 degrees C. If there's a 1 in the first position, it's from minus 55 to 125 C. We're actually going to be using this basically at room temperature, so it makes no difference. This first circuit over here, we've got feedback to the minus terminal. So this comparator looks like it's being used as an op-amp. We'll take a look at that in just a little bit. Here I've got the feedback going to the plus terminal, so that's positive feedback. And this is one of our hysteresis loops. And then here I got a comparing of two voltages with no feedback around it, so this must be used as a comparator also. What else can we say about the schematic as we look at it? Well, let's see, we write down a few things here. Here's the power supply, which is set to 30 volts, and here I've got half the power supply, so I've got 15 volts here. And over here, I have basically no current going into the terminal of the comparator or op-amp, and so the voltage here is going to be half of the voltage here. So this is half of whatever this control voltage is. All right, let's do a simulation, kind of see what it does, and then we'll kind of chip our way into the equations of what's going on. Now this is an oscillator. It's actually going to change as we apply a DC voltage. That's what the V sub C is. This is my PSpice file. And a couple things to point out. Whenever we're doing an oscillator, we might want to turn on the power supply with a delay pulse. So if you just apply power, Spice just does it as a pre-initial condition check, finds all the initial conditions in the circuit, and basically it'll just sit at one point and won't oscillate. So putting a little time delay on the power supply will actually kick it into our richness in harmonics and get it to oscillate. So I delayed it just 1 nanosecond. Now when doing simulations with a lot of parts in it, like this, I got 3 of my macro models. If I had the full chip simulation, it's not clear to even get convergence. But one of the things you're going to run into when you're doing a lot of parts is that sometimes you'll be iterating an answer and all of a sudden the program will just quit. It says can't find the answer. And it really has to do with one of the artifacts of the original program. To save time and to save money in the 1970s, the program stopped itself from running too long. Whenever you're iterating at a point in Spice, it tries up to 10 times. And if it can't find an answer, it just quits. Well, we could let it go a lot farther than that. So I played with this as I was doing this problem and I had to kick it up to 400. So at any one point as it's solving for an answer, it can do up to 400 iterations before it'll quit. Now this is also going to slow the program down. It's going to take longer to run something because almost every point it's going to do it at about that rate of 400 iterations. But you have to play with that. So just to get the word of warning in the future as you run simulations, if all of a sudden everything quits, it's the term ITL4, and that's the number of iterations per point in a simulation or a transient analysis simulation. Let's take a look at what the output looks like for this. And let me just scroll back here, just going to point out which terminals are which here. So the output of this circuit over here, which looks like an op-amp circuit, this is node 5. Here's node 9, and here's node 4. We'll first take a look at nodes 5 and node number 9. In this first simulation, I set that control voltage battery at the far left of the schematic to 30 volts. This is the output of the linear circuit. It's just a ramp, then another ramp, not as long, and then repeating and repeating and repeating and repeating, where the slopes here look like they're the same. This is the output of the hysteresis loop circuit, and it's roughly going to about 30 volts here and 0 volts. So after some transient analysis, we see there's a steady state square wave that's coming out of our comparator, and then what's coming out of our linear circuit is basically a series of ramps or triangle wave. The period of this in steady state is about 13.25 microseconds, and that would give me a frequency of 75.47 kilohertz. I ran the simulation again, but this time I made the control voltage 15 volts. And you can see it takes a little bit longer for the transient analysis, and then in steady state we're again getting this same slope, but just changing the sign of it as we're going on with time. And our output's likewise going from 0 to about 30 volts. Now the period is 23.299 microseconds, which is a frequency around 42.92 kilohertz. So as we're varying this controlled voltage, we're changing the frequency of the output of our circuit. So this is some kind of a voltage controlled oscillator. Let's see if we can figure out how this thing works. Let's first take a look at what that second comparator is doing. So I redrew that part of the circuit where I've just got the voltage divider here just represented by a battery of half the power supply. Let's assume that this comparator just saturates between 30 volts and 0 volts, since we have a 30 volt, 0 volt power supply. And I've got two resistors here, a 5.1K and a 100K. And if you look at the circuit long enough, this is exactly the circuit we did in supplemental problem 6.4, the non-inverting hysteresis loop. So let me go grab the equations from that supplemental problem. The resistor here was called R1, and this was called R2. So in our formula now, replace R1 and R2 by R7 and R8. And the sum of the two saturation voltages. Now this is 5.1K, this is 100K. This is roughly 30 volts, this is roughly 0. So I'm going to get a width of my hysteresis loop about 1.53 volts. We're going to go plus or minus half of this from the center, so let me just divide that by 2, so it's 0.765 volts. Now the center of hysteresis loop, we can go grab that formula. It's V sub R, the reference voltage, which is 15 volts here. And then we have the resistor R1 over R2, and then that'll be 7 over 8. Likewise over here. And then the differencing of the saturation voltages. Okay, this is 15 volts, 5.1K, 100K, same thing here. This is a minus 30 volts, and this would be a plus 0, and then divided by 2, and I get 15 volts. So the center of my hysteresis loop is about 15 volts, plus or minus 0.765. So 15.765, and then subtracting that, I get 14.235. Again, this is a non-inverting hysteresis loop. We're going to come this way, come up this way, can go back out, and then come back down this way. Let's take a look at that third comparator. The plus terminal on this one is being fed by node voltage 9, which is our output from the hysteresis loop circuit. And then the other terminal was the voltage divider of a half. And so when the voltage across here is positive, then the output transistor is cut off, and there'll be no current flowing in here. When this voltage is negative, this becomes a short back to ground. So let's take a look at that case first. In other words, when V9 is less than 15 volts. So if this is basically a short back to ground, the current that flows in here, which is going to be part of the circuit with the LM339 number 1, is going to be a difference of these two node voltages. Now this is hooked up to roughly a half of the controlling voltage, V sub C. Now that will be a DC voltage, or it can be a slow changing value too. And so this node voltage minus this node voltage divided by the resistance would be the current. But with this pulled down to 0 volts roughly, then we just simply have 1/2 the control voltage minus 0 over this resistor R10. So we have 1/2 V sub C over R10, where R10 is a 50K resistor. Take a look at that first comparator, which is operating in a linear circuit. So here we've got negative feedback around here, so it's actually going to be a stable circuit. And we'll talk about how we're going to do that with the 339 comparator a little bit later in the lecture. So our integrator is going to take the integral of the current in the capacitor. So it's going to be 1 over C, integral of I is C1 dt, plus whatever initial condition we have. Now what we want to do is we want to solve for node voltage 5. And so node voltage 5 would be a rise in voltage if we went around the loop this way, and then we'd have a negative drop, so the drop across the capacitor, plus 0, plus we have half of the controlling voltage with the voltage divider on the input. What's the initial condition here? Well, when I ran the simulation, I didn't use the command on the .tran line called UIC, which is user initial condition. Now when you don't specify that, what the program does is it open circuits all capacitors and short circuits all inductors, although we don't have any. It finds the initial condition. If you put the UIC letters at the end of .tran, and it will do what's called the user initial condition, and if you didn't specify any initial condition for a capacitor, it would treat it as 0. Well, let's just figure out what that initial condition must have been. Well, at time t equals 0 plus for this node voltage, we had 0 volts out. So if you go around the loop here, minus this voltage plus 0 plus V sub C over 2 has to equal 0. That means that the voltage across here must be V sub C over 2. That's my initial condition. So we go back to this equation up here. I'm going to have a negative of this and then a positive of it, so they drop out. So what we saw was that we were integrating starting at basically 0 volts. So let's take a look at solving for I sub C1. The output of our integrator is node voltage 5. And where's this starting out? Well, we know at t equals 0, or 0 plus, it's equal to 0 volts. So if you go look at the hysteresis loop on the previous page, when V5 is equal to 0, V9 is equal to 0. There's a unique answer. We're not into the hysteresis loop. Okay, if that's the case, then the comparator on the bottom, it looks like a short, and we're drawing current into that bottom resistor. So let's go back and calculate the currents that are now going to flow in that integrating capacitor. Okay, so this capacitor current here is equal to this current plus this current. So it's the current in I sub R1 and then minus I of R10. So what's the current in here? Well, it's going to be this node voltage V sub C and this node voltage here, because I've got 0 volts here, of 1/2 V sub C divided by R1. And then we derived an expression for the current in R10 when the comparator was low. And that's the expression right here, 1/2 V sub C over R10. We'll take the difference of those two. Now R10 is half of R1. This was a 50K versus a 100K resistor. Let's take the difference of those two. So here I've got the difference of these two, which is going to be 1/2 V sub C over R1. And then I have 1/2 V sub C, and then I have 1/2 R1. The 1/2s cancel, and I get V sub C over R1. So the difference of these two is 1/2 V sub C over R1. So that's the value of the current that goes into that integration equation on the previous page. The two minus signs cancel, can bring out the 1/2, and actually bring out the V sub C over R1. And we're taking the integral of 1 dt, which is going to be equal to just t. So my response looks like 1/2 V sub C over R1 C1 times t. So in other words, a positive ramp. That's exactly what we saw in the simulation on page 29. Now this keeps increasing until we hit the edge of the hysteresis loop. And for a 30 volt value of V sub C, we're going to reach that hysteresis corner when the voltage at the output of the integrator is 15.765 volts. So how long will it take to get to there? Well, I can just take this previous equation and solve for the value of t when V5 is equal to 15.765. So 15.765 divided by 30 times 2 and then times R1C1. That's 52.55 microseconds. That's about what we saw on page 29 when all of a sudden things started to change. So when we get to that corner of the hysteresis loop, the voltage V9 now goes from 0 volts to 30 volts. And that bottom comparator now, its transistor is cut off, so the current I sub R10 is equal to 0. So now the current in the capacitor is just the current in the resistor R1, which is the left side minus the right side. So it's our control voltage minus 1/2 our control voltage over R1. So it's 1/2 V sub C over R1. So if we go back to our initial equation now with initial conditions, we had, this was our expression. And now what's the value here? Well, what's the value of this voltage just before we switched? Well, on one side it's V sub C over 2, and then on the other side of the capacitor it's V sub 5 of T1. So the difference of those two is the voltage across the capacitor at times T1 plus and T1 minus. Okay, so let's put that in. It's 1 over C1. Bring out the I sub C1. The integral of 1 dt is going to be just t, so it's going to be the upper limit minus the lower limit. And then we're going to subtract this term here, so minus V sub C over 2. And then the voltage here was 15.765, so we're going to subtract that. And then we're going to add V sub C over 2. So these two are going to cancel, and we just get the expression here. So I've got a minus 1/2 V sub C over R1, then C1, and then T minus T1, and then 15.765. So now we're actually changing the slope of our integration. We had an initial condition, and we're now going down. And eventually the voltage is going to jump when we get to V5 getting to 14.235 volts. That's going to happen at some time, say t equals T2. So let's solve for it. So let's plug in here t is equal to T2 and set this equal to 14.235. So I'll bring this on the other side of the equation, so I get a minus. I'm going to divide by this, which is minus 1/2 30 volts over R1C1. When you multiply all that out, you wind up getting 5.1 microseconds. So that the interval as we start to integrate with the negative slope is equal to 5.1 microseconds, much shorter than the first one because we had to get to an initial corner on the hysteresis loop. Okay, now when this happens, the comparator changes state on the bottom, and now we have again the bottom resistor drawing some current, and we're back to our original expression again. But now the initial condition here is going to be on the left-hand side of that capacitor, V sub C over 2. On the right-hand side now, 14.235, so the difference of those two. think we're going to get a cancellation of this term with this one. What we have then is minus 1 over c1, the integral of I sub c1, integral of 1 dt, so upper limit minus the lower limit, and just this term of minus 14.235. Now the value of I sub c1 is what we found initially. It's minus 1/2 v sub c over r1. And now we can complete the calculation here. We've got plus 1/2 v sub c over r1 c1, t minus t2, and then now a plus 14.235. So now we're integrating back up again. How long does it take for this voltage to get to 15.765 volts from our start point of 14.235? Well, we can solve for it. Set V5 equal to 15.765, subtract the 14.235, and then divide by this stuff. So it's going to be 1/2 v sub c over r1 c1. Okay, v sub c is 30 volts, r1 c1 is 100k, 500 picofarads, and we can get 5.1 microseconds. The interval we're integrating down is now the same as the interval we're integrating up, so we're going to get a repeatable square wave out of this, as we saw in the simulation. And so our frequency then is going to be the sum of these two times, reciprocal, and that's going to be about 98.04 kilohertz. We'll see in the data sheet that says it's about a 100 kilohertz oscillator. Now, can we derive a general formula for this? Now, if you look at this and do it symbolically, you could figure it out, but it gets a little tedious here. But if you look at what's going on here, the term over here, this is the width of the hysteresis loop. And we have a formula for that. That's R7 over R8, saturation plus saturation minus. And we're dividing by this term over here. So we're going to have a 2, and I'll explain where the other 2 comes from. R1 C1 divided by V sub C. Now this is for half of the period, so just double it for the period together. So we could predict now for any value of V sub C what the time is going to be. Well, how does this all compare? Let's just kind of summarize the data here. For control voltage of 30 volts, my upper trip point was 15.952 in the SPICE simulation. My lower trip point was 14.037. The period was 13.2 microseconds, and the frequency was 75.47 kilohertz. Using this formula, or the calculations we just did, it's 10.2 microseconds for the period and 98 kilohertz for the frequency. So why are we off? Well, we got a non-ideal comparator, and we're starting to see the effect of time delay and rise time and fall time. So that response time of the comparator. Now, if you slow things down, we should get less error. So here was the second simulation. My upper trip point was 15.912, 14.125 for the lower. Period was 23.3 microseconds. Frequency was 42.92 kilohertz. Using the formula above, I calculate 20.4 microseconds for the period and 49 kilohertz for the frequency. You can see here that the errors are beginning to decrease. I ran another simulation with 3 volts, but didn't show the data because it was going to get too long. But just here what I measured, 15.783 for the upper trip point, 14.235 for the lower. Getting close to what we hand calculated. Period of 105.1 microseconds in SPICE and a frequency of 9.51 kilohertz. And then I calculated the period and the frequency from my formulas. Got 102 microseconds for the period and 9.8 kilohertz for the frequency. You can see the errors begin to decrease as we slow down. You could also get a faster comparator, and you would get more, again, idealized results. So we do have a voltage-controlled oscillator. Now, how are we going to implement this thing? Now, back on page 23, we talked about the LM339 comparator having an open-loop curve with many poles, and so it's unstable with resistive feedback or capacitive feedback too. Let's take a look at the data sheet and see what they did with this particular comparator to make it into a stable integrator. So here's page 10. You can see it's a circuit we just talked about, but there's something added here and something added over here. Let's go back and figure that out. So what we've got here is some kind of a compensation network, and likewise a compensation network over here. Let's see if we can figure out what these are doing. Let's first take a look at the R4C2 combination. This is how it's interconnected into our circuit, where that comparator number 1 was acting as an op-amp. Now, if you recall back in the chapter, we talked about the transistor here being either cut off or saturated. But if this is used in an op-amp, this transistor is going to go active. So we have some equivalent circuit at, say, low frequencies. So our model roughly was to have a current source here of GM V pi. So put that down for transistor 8. If we're doing an AC analysis, the DC power supply is just shorted. So we're going to short that back to ground, so we have R4 back to ground. And then we got this capacitor C2 in parallel with that. Okay, well, what is that doing? Well, there's a voltage here. It's going to be equal to the current in this direction times the impedance that's here. So it's going to be GM8, say V pi 8. Let me write this parallel combination as the sum of two admittances and then take the reciprocal to get the impedance. So SC2 and then 1 over R4. Now multiply numerator and denominator by R4 and we get this term here. And then we're divided by SC2 times R4 plus 1. And all that's times V pi 8. What's going on here? Well, this is actually our form of a pole. And there would be a pole at, if this was J omega divided by omega C. Omega C would be 1 over R4 C2 and then divided by 2 pi to get the frequency. With a 0.01 microfarad capacitor and a 3K resistor, we're looking at about 5.3 kilohertz. But what this is doing is introducing a pole. So at lower frequencies, that caps an open circuit and we get some kind of open loop gain, which we know is around 106 dB from the datasheet. And that this is creating a pole at about 5.3 kilohertz. So now what we've done is we've actually added a dominant pole to the system. Because inside the comparator, there are a lot of transistors, but their poles and zeros show up in the megahertz range. And so we're introducing a dominant pole with an external capacitor, just like the 741 had it internally. Let's see if we can figure out what the beta circuit looks like for this integrator. So set the source equal to 0. We're going to add this R sub x and C sub x. We'll talk about what that's going to do in just a little bit. And then what was going on over here before? Well, we had a current source in parallel with an R and a C. But for my beta circuit model, I've got to have a model here of some kind of a voltage-controlled voltage source. So why don't we do a source transformation? So here I've got my R2 in parallel with R3. I've got a resistor R1 going back to ground. I'll talk about this in just a second. And then I'm going to find the voltage across these terminals where I've got the R sub x and C sub x with the opposite polarity. That's part of our beta network test. I've got a capacitor here, but now if I did a source transformation here, I would have a series element that has C2 and R4 in parallel, and then that's in series with a voltage-controlled voltage source, which should be part of my open loop gain. So replacing that by a voltage source and solving for the voltage across here, that would be my beta network result. Now back over here, this was connected to the bottom comparator that was either an open circuit or a resistor back to ground. And that resistor was R10, that 50K resistor. So I'm going to do the simulation twice, where this is an open circuit and then when it's equal to 50K. Now we could analyze the circuit. I've got 1, 2, 3 capacitors and could approximate it with the one capacitor method, but you know what, why don't we just run a simulation and see what the voltage here looks like in terms of this voltage, and then we can see whether we have a good rate of closure or eventually calculate a phase margin. So the first simulation, I guess I'm going to do the 50K case first, and then I'll do it again with an open circuit basically. Let's see what happens. I'm going to sketch 1 over beta. Now the voltage between nodes 2 and 4 is actually the voltage divider of our value of beta, so the reciprocal of that would be taking it negative in dB. So I'm getting a positive dB here for an attenuation circuit. You see here how it varies with frequency. Now, what does the open loop curve look like? I'll talk about the red one in just a second. Well, we figured out that this RC circuit created a pole at 5.31 kilohertz. So let's just sketch that in. We've got some open loop gain, which we know is about 106 dB, and then now we've got a pole around 5.31 kilohertz. And you can see that the rate of closure is very good. We're coming back into that flat, and so our rate of closure then is the slope of 1 over beta minus the slope of our ADM curves. It'd be plus 20 dB per decade. So a very good rate of closure. Now the actual splice model had a pole at 2.17 kilohertz. That's going to move this over a little bit. And likewise too, that has a good rate of closure. So when we did the simulation without this added networks, we got a good result. And so that's consistent with that. Now I went back and I ran the simulation again, but now with R10 as an open circuit. See if things get better or worse. You can see here that it actually is a little bit better. We're actually running into it where this is coming up. There's a slight phase shift as this thing's coming back and leveling out again. But in both cases, the rate of closure is very good. If you were to include the simulation model, it would also look pretty good too. And this is an analysis of a voltage-controlled oscillator.